Let's take a look at this example. Here we're asked to find the area of the graph bounded by the graph of f and the x-axis on the given interval. And our given function is f of x equals sine of x. And we're looking for the area on the interval from negative 3 pi over 4 to 2 pi over 3. Now, I capitalized the word area here because this does not say find the net area. We know that we could find the net area using the fundamental theorem of calculus and using f of b minus f of a, because the fundamental theorem of calculus calculates net area for us. But here we're not asked to find net area, we're asked to find the total area. So what this means is whether the area between our function and the x-axis lies above the x-axis or whether it lies below doesn't matter. We're going to count any area, whether that area is below the x-axis or above the x-axis, as positive area, because we just want to know the total area, not the net area. So as we know, the first step in this is to find the area function. To find the area function, we integrate the given function. When we integrate sine of x, we get negative cosine of x. And again, I want to make this distinction one more time. At this point, if we wanted to find the net area between the graph of sine of x and the x-axis, we would use the fundamental theorem of calculus. And we would just evaluate this negative cos x from negative 3 pi over 4 to 2 pi over 3 using f of b minus f of a. That would give us the net area. But we want the total area. So the first thing we're going to do is break this interval up into two separate intervals, because we're going to find the area from negative 3 pi over 4 to 0, and then make sure that that area is a positive area, because it is area. And then we're going to do the same thing, and we're going to evaluate this from 0 to 2 pi over 3. And if that value is negative, we're going to make sure it's positive. And then we're going to add our two positive areas together to get the total area for this function on this interval. So here's essentially what we want to do. We want to take this area and add it to this area. And we're going to take a step along the way to make sure that both of our areas are positive values. So let's start by calculating the area of negative cos x on the interval from negative 3 pi over 4 to 0. To find that area, we evaluate negative cos x at the upper limit of integration, which is 0, and then subtract from that negative cos x evaluated at the lower limit of integration, which is negative 3 pi over 4. Cosine of 0 is 1, so the opposite of that is negative 1, minus cosine of negative 3 pi over 4 is negative root 2 over 2. But then negative cosine of negative root 2 over 2 is positive root 2 over 2. So now we have negative 1 minus root 2 over 2, which is a negative value. And we should expect this because the graph of sine x lies below the x-axis on the interval from negative 3 pi over 4 to 0. So we should expect this to be a negative value. But because we want total area, not net area, we're going to make this negative value positive. And we can do that by negating the negative area. So we'll negate negative 1 minus root 2 over 2. That gives us the positive area of 1 plus root 2 over 2. Now let's find this area. So we evaluate the area function at 2 pi over 3 and subtract from that the area function evaluated at 0. Cosine of 2 pi over 3 is negative 1/2, and the opposite of cosine of 2 pi over 3 is positive 1/2. And we subtract from that the opposite of cosine of 0. Cosine of 0 is 1. The opposite of that is negative 1. So we have the expression 1/2 minus a minus 1, which is the same thing as 1/2 plus 1. Because this was a positive area to begin with, we don't have to make any adjustments. So now we're going to add our two positive areas together to get the total area. So we'll have 1 plus root 2 over 2 plus 3 over 2, which equals 5 halves plus root 2 over 2. And because we have a common denominator, we'll combine these two terms into a single term to get our total area, 5 plus square root of 2 all over 2. When we complete problems like this now, it's really important to know that I didn't just make up the two different intervals. In other words, these two different intervals didn't just come out of thin air. I deliberately chose the interval from negative 3 pi to 0 because I knew the graph of sine of x was all below the x-axis from negative 3 pi over 4 to 0. I also knew that the graph of sine of x was all above the x-axis from 0 to 2 pi over 3. So this means that when we're defining our intervals to find total area, we need to group our intervals in such a way that one interval lies entirely above or below the x-axis. The next interval lies entirely above or below the x-axis, and so on. But to be able to do this, we have to know where the zeros of our function are. So if we were asked to find the total area of a function whose graph looked like this, we would need to group the positive areas together and the negative areas together. Here's what I mean. We can see that the graph of the function from negative 7 to negative 3 has a positive area. So our first interval of integration would need to be from negative 7 to negative 3, and we should expect that value to be positive. The next interval would be from negative 3 to negative 1/2. And we can see that the graph of our function lies entirely below the x-axis from negative 3 to negative 1/2, so we should see a negative area there that we would then make positive so that we could get total area. And then the last interval would be the interval from negative 1/2 to 5. This function on the interval from negative 1/2 to 5 lies above the x-axis, so that would be a positive area, so we wouldn't have to make it positive. But I'm saying this because we have to intentionally pick the intervals according to whether our graph is entirely above the x-axis in that interval or whether it's entirely below the x-axis in that interval. And here's why. This drawing over here on the right is a new function, the graph of a new function that we want to find the total area of. If I define my first interval for this function to be the interval from negative 5 to 0, when I use the fundamental theorem of calculus to do that, you can see I'm going to have a net value from negative 5 to 0 because I have some positive value area and I have some negative value area. And the net area for that region won't give us an overall accurate picture of the total area. So what we would need to do is define our intervals from, say, negative 5 to negative 2, because that portion of the graph is entirely above the x-axis. Our next interval would be from negative 2 to positive 2, because that interval is entirely below the x-axis. And then our last interval would be from positive 2 to positive 5, because that area of the graph lies entirely above the x-axis as well.